Hello friends, it's Ben again. This is a video for the vector calculus class. This is a video for the vector calculus class. The topic we're covering today is exact differential equations. Exact differential equations are going to seem pretty familiar to y'all, and it's really kind of the connection with the differential equations class and the vector calculus, because essentially what you're doing for these exact differential equations is you are constructing a potential function. So it really has to do with conservative vector fields. So it's not quite in exactly that format, but it kind of is. So, all right, let's take a look at our definition stuff here and see what we can get going. And yeah, go. Yay. All right. So with exact equations, here is a quickie example of something new that we cannot handle with the previous techniques. This equation, 2x plus y squared plus 2xy times the dy dx, if you tried to solve that as a linear equation, you couldn't, because we've got that y squared in there. That means it's not a linear equation. And we also have the multiplication of y times dy dx, which also makes it nonlinear. But this 2x or any functions of x are not going to make it be nonlinear. Okay. So we might instead try to solve it by treating it as a separable differential equation. But when you solve for dy dx here, notice that on top you get this 2x plus y squared. There's no way that you can factor that into a function of x and a function of y. So unfortunately, we just can't get this one to be solvable through either one of those. However, some equations, and these equations we call exact, some equations you're able to get a solution of the form psi of xy equals c, and have the psi sub x plus psi sub y dy equals 0 be, your equation here. And in that case, we usually have the labeling where we write it as m plus n, and having the m and n both be functions of x and y. But m plus n dy dx is equal to 0. Or alternately, you may also see this written, and I should just real quick write this off here. You may see this written as m dx plus n dy equals 0, which again, because this relates to that notion of finding a potential function, should look kind of familiar to you, and maybe even explains the reason why we write those line integrals in that particular way, maybe. So in any case, if we label the two functions as m and n, then we can check to see whether we've got a conservative vector field and therefore a potential function by calculating m sub y and n sub x. If they turn out to be equal, then you can find the potential function by just doing the appropriate integrals. Okay, so that gets that. Let's try this. All right, so for this one here, we're going to have to separate the pieces, and we'll label this as m and this is n, and then we'll go over here and check. We had to check m sub y. When you do that, the 2x will disappear and you'll get just 2y. And then we'll take the n sub x, since that's 2xy, then when you do that with respect to x, you'll get just the 2y. So yes, we do in fact have a conservative vector field that we can get a potential function for. So you'll take the 2x plus y squared dx and get x squared plus xy squared plus some function of y, and then we'll do the other way, the 2xy dy, and that will get you xy squared plus some function of x, keeping in mind that so far as x is concerned, y is a constant and vice versa. So the g and the h are really just replacing the constants that you'd normally have. So now our function f of xy, that's our potential function, we just piece it together and say the xy squared that appeared in both of them, and then the x squared that appeared in one of them. And then you could say plus c here, or alternately, since what we're looking for is getting a solution, say equals c like that, okay? And I think I went ahead and put this on Desmos already. If I didn't, this may get a little bit slow. Let's see. And so here we've got the x plus xy squared on there. And I've put a c value in so that we can do some manipulation of it. Now, as you'll notice there, we are clearly getting out of our solution there stuff that that has kind of a fold in it. You don't have a function per se because of the fact that you've got two y values corresponding to the same x value. But if we have c values coming down here, so for the negative c values, you can take the upper branch or the lower branch and have a solution that you're solving in terms of. So I'm going to jump back over to my notes app here and take a look at what we would do on getting a solution there. If you wanted an explicit solution, you know that you would have to take the c minus x squared, divide it by the x, and then get that your y is plus or minus the square root of c minus x squared over the x portion there, okay? And so you can clearly see from that having x equal to 0 is going to be a bad idea, but we could have seen that from another direction as well. If you had taken and solved here and gotten dy dx equals the 2x plus y squared. Oh my gosh, I had this written on the previous page, didn't I? Okay, sorry. But if you solved like that, and we had talked about that this function of x and y needed to be continuous in the neighborhood of your initial conditions. So this here says that our initial conditions cannot have the y being equal to 0 or the x being equal to 0. And as a matter of fact, you also need the partial derivative of this with respect to y being equal to, or being continuous as well. So we might actually crop up with some other sort of things about it. But because of the fact that you can't have your y being equal to 0, that's this indication that your initial conditions need to be away from the x-axis, which is the place where you get it kind of doubling over in the graphs that we've taken a look at there. So, all right. The essential thing that we needed to get down to for a solution here, though, was going to be this part right here. Okay, that's what we've got for our general solution. Yeah. So let's go ahead and take a look at another one of these. So this one looks kind of horrifying, right? It's got your y cosine x and plus 2x e to the y. Ugh. So polynomials trig functions and exponentials all mixed together in a wonderful soup of stuff. All right, we're going to check it real quick. As per usual, call this M, call this N. I used y prime instead of writing dy dx this time. Hopefully it doesn't confuse people too much. Then we're going to take our m sub y, and we will get cosine x, because the y went away, and plus 2x and e to the y. All right, and then we'll take n sub x, and we will get derivative of sine is cosine, looking good, plus 2x, and leave the e to the y alone, and then the minus 1 will go away. So we do, in fact, have these things turning out to be equal. So that says that we do have a conservative vector field. We can get a potential function. And so we just tackle that. So y cosine x plus 2x e to the y, integrate with respect to x, and let's see, y sine x plus x squared e to the y plus g of y, and then we'll come down here and do the other one, the integral of sine x plus x squared e to the y minus 1 dy. And so you'll pick up a y here, the y sine x, and the x squared is left alone, and the e to the y is left alone, and then a minus y plus h of x. So it turns out this time you're just picking up that, but we can see where we've matched up the other pieces. Our f of xy here is just going to be y sine x plus x squared e to the y minus y, and then we'll set that equal to a constant. Okay, so like before, the answer we're really looking for is just this here. And I was wanting it to highlight that. Darn it. Maybe if I do it in blue, it'll look nice. Yay. Okay. So jumping over to Desmos here, we'll turn off the previous graph and turn this one on. And notice it drew me nothing, right? So this is actually going to be a kind of a weird one. So when the C value is equal to 0, it's got kind of this weird little teardrop shape there. As we push this down, notice that things kind of materialize from below and they join and come together, and weird, right? So what is that really representing? Well, we have some sort of a three-dimensional graph. We could probably look at the Calc plot 3D function and give it this graph and see what's going on. But it looks like for these very low values there, that you've got kind of a line. So it suggests that whatever this surface graph is, it's got kind of a little valley down there on the positive y-axis. And then as you get up higher, you start having other valleys join up. Yeah. And I would guess that in the first and second quadrants there is where you're having the highest values coming out for your C. So I have to be honest in saying I don't see that there was anything useful in what I just drew for y'all. Okay, but the technique that we got out for this is going to work no matter what you're dealing with, so long as you have something that is exact. So let's look at something that's not exact. And in particular, what we're going to look at here is an integrating factor. Remember how with the linear equations, they had something that you multiplied through and it made the left-hand side into a product rule kind of thing. So the same thing happens with exact equations, that sometimes you're able to find a factor that you multiply through. Unfortunately, things will not be as organized as they were for linear stuff, because it's often talking about nonlinear stuff, and nonlinear stuff is just harder. It's just, I just had to be honest with that. So if I go ahead and say this is m and this is n, and we check, then m sub y turns out to be 3x plus 2y, and n sub x, excuse me, turns out to be 2x plus y. Clearly, those are not the same thing, right? So not equal. But this suggests that if we multiply through by x, that maybe it will become. So I'm going to take x times m sub y, and so that's going to be x, I'm just going to multiply it through there. 3x squared y plus xy squared. And then we're going to take the derivative with respect to y. So we have 3x squared and plus 2xy. And then y sub n, I'm sorry, y times n and then sub x. So we've got to think about that's x squared y plus 2, not plus 2, plus x. I'm sorry, folks. Back up. I wrote the whole damn thing wrong. It is supposed to be x being multiplied by the n. And then we'll do it with respect to, damn it, x. So that is x cubed plus x squared y with respect to x. We get 3x squared plus 2xy. And so those two things were equal. So we do have a conservative vector field. So the key thing is that now we're solving a slightly different differential equation. When you multiply through by that x, then you do have the possibility, what if x is equal to 0? And that, you know, just introduces an additional possible solution there. So kind of like when you're doing things in a pre-calculus class and you square both sides and introduce an extraneous solution. So, all right, I'm going to take the xm here, and that was 3x squared y plus xy squared, and integrate it with respect to x. I get x cubed y plus 1/2 x squared y squared plus g of y. And then I'll integrate my x cubed plus x squared y with respect to y. I'll get x cubed y plus 1/2 x squared y squared plus some h of x. Turns out there isn't any g of y or h of x. So our f of xy that we're looking for is just the x cubed y plus 1/2 x squared y squared. And we want to set that equal to c. Okay. Now, when you're doing that, you might notice that you can do some factoring. So we can factor an x squared out of both sides, both factors, and a y out of both of them. And then you're left with x plus 1/2 y. Okay. So keep that in mind. In particular, when the C value is equal to 0, we're going to expect to see some specific things. When C is equal to 0, then we'd expect to have this as a solution. That'd be y equals 2x. And then this set equal to 0 as a solution. And then this set equal to 0 as a solution. Okay. Are there other things to talk about? Yeah, we are going to pop over here in just a second, but let me go ahead and write down, if we got the dy dx here of 3xy plus y squared divided by x squared plus xy. Notice that you can factor a y out of the top and an x out of the bottom, but you don't have common factors that cancel out. So essentially for discontinuity stuff, you want your x to not be 0. And then after you factor an x out there, you also want your y to not be equal to minus x, because both of those make discontinuities in that function there. So let's go ahead and take a look at the graph that comes with this. So I have the C values pushed up to 10 there. Let's put them to 0 if I can. All right, notice that you get drawn there the line y equals 0 and the line y equals minus 2x. I believe those were both things that we predicted there, weren't they? So yeah, right, because the y equals 0 and the y equals minus 2x came from these. There's also an x equals 0 that we're not seeing on the graph here, which is kind of weird. I really would have expected that to show up. But as we have positive C values, you can see that you have positive solutions there, the ones that are above the x-axis, and negative solutions. And there's a kind of a symmetry to them as well. So, but you also have a discontinuity that's happening there at x equals 0, which, remember, was something that we said that we couldn't have our solutions allow x to be equal to 0. And then we also didn't want the y value to be equal to minus x. And that is taking care of itself by the fact that the y equals 2x looks like it's getting kind of an asymptote going there or something, kind of a slant asymptote. Now, as we got negative C values here, notice that you're going to have your solution separating out there. It's kind of defining some kind of a hyperbola, right? But if you take a look at what's happening there, it's most prominent when it gets down close here. You would have different branches of solutions. So the stuff that is that's asymptotically going towards the negative x-axis there would be one branch, and then stuff that is going up towards y equals negative 2x would be another branch for the stuff in the second quadrant. And then in the fourth quadrant, you've got kind of reflected the same kinds of things. So, all right. So the main thing that we're seeing out of this, though, is that some problems, if you know what to multiply them by, it will make it into an exact equation. And you should rightfully be saying, well, how the hell am I supposed to know what to multiply by? Well, here's a trick. This doesn't get all of them, but this is characteristic of the type of things that are going to crop up, okay? So if you've got an equation in this sort of form of of an exact equation. And if it turns out that it's not exact, but that you can multiply by something to make it exact, then that means that you need to have these partial derivatives turn out to be equal. I am a little dicey on getting the algebra of this step here to work, but it will turn out that the derivative of mu with respect to x will turn out to be m sub y minus n sub x all over n, and then times mu, okay? See if y'all can work that out. I couldn't quite make the algebra work out nicely. So, sorry. But if that is the case, and if this piece right here is a function of x, if somehow all of the y's cancel out, then you have a differential equation in x that defines mu. And as a matter of fact, it's a separable differential equation. So you'll be able to divide that mu out and have your logarithm of mu show up over here. And then you just got to hope that the rest of this stuff here turns out to be something that you can integrate, right? And maybe has a log in it. So if this m sub y minus n sub x over n turns out to have to be a function of x alone, then you can find out your integrating factor this way. So we'll see an example of that. There are often other ways to find integrating factors. This is something I'm not super fond of about differential equations, is there are roughly 15 quintillion tricks, and it doesn't seem like they're always very organized. So, all right, let's take a look here, and we're dealing with this one, and we are going to refer to the m here and the n here. If you go ahead and check the m sub y, oh, by the way, this should be obvious, but that's a 2. My handwriting was a little iffy there. But your m sub y should end up being x plus 2 times the cosine of y, and your n sub x should turn out to be just the cosine of y. I wrote that badly. Just the cosine of y, and those clearly are not equal. So we need an integrating factor in order to make this work out. So we got to remember that notion, d mu dx equals, man, what was it? M sub y minus n sub x. So, and then divided by n, and then times mu. So let's write those down. So the m sub y, oh, well, hey, it turns out that we just did this work, right? So strangely enough, that work was not wasted. And then times mu. So d mu dx is equal to, if you look there, you can factor a cosine out, and this turns into x plus 1 cosine y divided by x cosine y, and then the mu. The y's cancel out, and we have a function of x alone. So then you'll say d mu over mu is equal to, I'm going to simplify this as 1 plus 1 over x, and then dx, and then we'll integrate. And that says that the log of mu is going to be equal to x plus log x plus c. And then we're going to exponentiate and get mu equals e to the x times e to the c, or as I am wont to do, just c with a different font. So cxe to the x. Now, here's a great thing. Remember when you were doing the linear equations before, we dropped the plus c that came out of that integration. And the reason we could do that was that there was going to be a factor of e to the c that went throughout the whole problem. And so you could divide it back out. Same thing applies here. So our mu that we're looking for is just the x e to the x. We don't need to worry about the c. So now our new equation, and this should look a little bit intimidating here, I guess, is going to be x e to the x times x plus 2 sine y dx plus, let's see, when you take x e to the x times that x cosine, you'll have x squared e to the x cosine y dy equals 0. Now, checking here, we have to take, I did not draw my bracket large enough. We need x e to the x, x plus 2 sine y, the derivative with respect to y. It's going to be x e to the x, x plus 2 cosine y. And then we have to take the derivative of this other part here, and we have to product rule it, but it does turn out that we end up getting that in the end. Okay. I don't want to waste the space on writing that, because I realize we're already going to have to go to another page in order to get this all to come out. All right. So let me grab this and add a page, paste it, and go up here. So once we have established that what we have is actually, lost my train of thought. Once we establish that we have something that is exact, then we can go ahead and do the integral of x e to the x, x plus 2 sine y dx, and see what we get. Oh, that's going to be a mess. And also do the integral of x squared e to the x cosine y dy. Okay, one of these is not going to be bad. And so, you know, guess what? I'm going to do the easy one and have my sine y plus, then we need to say something about an h of x here. Now, that integration there, because I do not want to bore you, I am going to step over here. I guess there's, yeah. I'm going to share screen, and guess what I'm going to use? Our good friend Symbolab is going to help us out with this. We need to be integrating x e to the x times x plus 2 sine y. You know what? Y, the y stuff I can just factor out. So I'm going to just say dx. I'm going to go ahead and have it integrate out there. And lo and behold, it turned out to be something nice. It turned out to be x squared e to the x, and then the sine y we would have sitting out to the side, and then I would say plus a g of y. And that means that if I go back and share again, okay, I was just afraid it was going to fail on me right there, because that would have been bad. So that means that our potential function, f of xy, we're looking for is x squared e to the x sine y. We would set that equal to c. If we had an initial condition, we could plug it in and just find out what that c turns out to be. But failing that, you could say that you have c e to the minus x and divided by x squared here, and say your y is this inverse sine c e to the minus x over x squared. Keep in mind, inverse sine is not nice, so we can't distribute it through to multiplication or division or anything. But we have a solution. So which solution do I want to see? Well, for the purposes of this kind of stuff here, just leave it in that form there. Okay. But if you need to actually use it in some engineering application, you'll probably have to solve for y. But in that case, you will probably also have some kind of an initial condition, and that'll make things a little bit less nasty because, you know, it's not just a general solution. Okay. So this gets you some examples here, and this is the kind of thing that we're doing. Shouldn't be too terribly rough because it's stuff you've kind of dealt with before, but that integrating factor, when you have to do that, that's, yeah. Look for stuff online and you'll find other tricks to get integrating factors. And that would be pretty neat to just share with the rest of the class, you know, if you've got more than one trick. All right, see you in class.